So you now have a good understanding of the factors that limit population growth. We're next going to look at a concept that ecologists use for understanding which organisms are most likely to succumb to those factors that limit population growth, and that is the idea of survivorship. Survivorship is the chance of an individual in a population surviving to various ages. Survivorship varies widely across species. For some species, an overwhelming majority die relatively early in life, while for other species, most die in old age. One tool for displaying survivorship is called a life table. A life table represents data on the chances that members of a population have of dying at each age interval in their lifespan. So, for example, this life table here displays data on the US population in 2011. On the left hand column, there are age groups, and in the very right hand column, it shows the chance of dying during that interval. So, for example, in 2011, there was a 0.001054 chance that a child aged 1 through 5 years would die. But looking toward the bottom of that table, there was a 0.788076 chance that someone aged 95 to 100 would die. Skimming the table, you can see that the age interval goes up, so do the odds of dying. This tells us that for people in the US in 2011, most people died in old age rather than in childhood. This information can also be presented in a graph rather than a table, and when this is the case, it's called a survivorship curve. The survivorship curve you see here is for the US population in different years. The percent survival is shown on the vertical y axis, and age is shown on the horizontal x axis. The leftmost life represents survivorship data from the year 1900. The one to the right of that is for the year 1950, then 2000, and then the last two lines are predictions about the years 2050 and 2100. As you can see, the survivorship curve for the US population is shifted over time. In the year 1900, there was a very steep drop off in survivorship for the youngest members of the population. This is reflected by the fact that in the year 1900, children under the age of 5 accounted for 30% of all deaths. Odds of dying young were much higher. This was an age before vaccines and antibiotics, and many young children succumbed to diseases that are now preventable and treatable. The advancements made in medicine are reflected clearly in the differences that we see between the curve for 1900 and the curve for 1950, which is unlabeled, but it's aligned just to the right of it, where we can now see that the odds of surviving childhood are dramatically better. So, survivorship curves are very informative about where the deaths in a population are coming from. This particular graph allows us to compare one specific population of humans, the US population, over time. But oftentimes, biologists want to look not at one species over time, but to compare the survivorship of multiple different species. The problem that you can run into there, though, is the fact that the different species can have very different lifespans. If we tried to gather the survivorship of a population of trout on here alongside the humans, it wouldn't make sense because trouts only have a maximum lifespan of 6 or 7 years. In order to get around this reality, that different species have very different lifespans, the x-axis can be changed from years lived to percentage of maximum lifespans. To the halfway point would represent the organisms that live to 50% of their maximum lifespan, whatever that is. Maybe it's 40 years if you're a human, maybe it's 3 years if you're a trout, but if you show it as a percentage, then you can place different organisms on the same graph to make a comparison. And that's what's being done here. We see three big groups of organisms represented here: humans, birds, and trees. And these three groups exemplify three different typical patterns of survivorship that are seen. We call these three patterns type 1, type 2, and type 3 survivorship curves. Species that fit a type 1 survivorship curve have a high likelihood of reaching a relatively high percentage of their maximum life expectancy. They have a high likelihood of surviving into old age, in part because they have few natural predators. Type 1 species tend to produce only a small number of offspring and invest heavily in raising them. Examples of organisms that conform to type 1 curves are humans, giant tortoises, and elephants. The inverse of a type 1 curve is that of a type 3 curve. A type 3 curve is observed in species that have a high likelihood of dying young. However, those that do make it past the juvenile stage are likely to live into old age. Unlike type 1, type 3 species produce large numbers of offspring, but have little to no investment in raising them. For example, a mackerel, which is a type of fish, can lay 1 million eggs, but on average only 2 out of the 1 million survive to adulthood. So it's a quantity over quality approach. Examples of organisms that fit the type 3 curve are frogs, insects, fish, and plants. Then finally, a type 2 survivorship curve is intermediate between type 1 and type 2. Type 2 species have a relatively similar likelihood of dying at any age. They are not particularly more likely to die in youth or in old age than they are at any other time in their life. Examples of organisms that tend to follow this curve are birds, small mammals, and small reptiles. In the next section, we are going to narrow our focus to humans and look at how some of their characteristics of their human population have changed over time.